Okay, so the next speaker, for all the mechanical engineering students in here, needs no introduction, but for the rest of you, it is Aamir Farooq. He is part of the Clean Combustion Research Centre here at KAUST. He received his PhD in mechanical engineering from Stanford University in 2010 and joined KAUST immediately after that. He's been promoted to full professor in 2022. He's the principal investigator of the Chemical Kinetics and Laser Sensors Laboratory here in KAUST, and his research interests are in the areas of energy, chemical kinetics, spectroscopy, and laser-based sensors. He's authored over 175 refereed journal articles and has given invited talks at a number of international conferences. He won the Distinguished Teaching Award given to the best instructor over a period of 2 years. In 2019, he was awarded the prestigious Hiroshi Tsuji Early Career Research Award by Elsevier and the Combustion Institute. In 2020, he received the Research Excellence Award by the Combustion Institute. He was recently elected a Fellow of the Royal Society of Chemistry. So thank you very much.
Okay, thank you, Jamie, for the introduction. Okay, so the title of my talk is Machine Learning-Enabled Spectroscopic Sensing. There was a very nice talk by the Professor Ellen and her student, so I'll contrast in which ways this is different. But we've been talking a lot about AI in this meeting and the advent of ChatGPT. So this is a ChatGPT-assisted presentation, okay? In some ways, but not quite. So I should actually, I asked ChatGPT that this is the title of my presentation, what should I do? It gave me a framework of 9-slide framework of how I should prepare this presentation. I didn't quite like it, so I didn't follow it. But it also said at the end, make sure to give references and credits, which it does not do itself, right? So listening to that advice, I should give credit to my students. This work was done by Imad, Mahanna, and C, so I'm thankful for their contribution. But anyways, we've also been hearing a lot that machine learning can do for us and AI, right? So I wanted to, again, put a couple of questions to ChatGPT and see its perspective. So the first question is, we've been seeing a lot of great stuff from machine learning and AI, and sometimes there was a talk maybe yesterday saying even it was doing better than human experts, right? So let's see what does ChatGPT think about that. It kind of gave a wishy-washy answer, giving credits to a lot of credit to itself, but giving some credit to humans as well. And I kind of find that interesting where it says that humans are very good. It puts the fields of art, music, literature, and psychology. So chemistry and energy are not quite there. So it probably thinks that it's better there. But at least at the end, it says that humans are indispensable. But I guess it's forgot to put so far, right? How it changes in future is to be seen. Okay, so the next question that I put to it is that related to my talk today, can AI assist the field of sensing? Okay, and what I like is that it starts nicely with a good definition of sensing, okay, and how sensing can be useful in process optimization and improving the performance of systems and all that. And then it gives a couple of ways of where AI can help, and I think those are quite logical and make sense. What I really like actually is that it puts in terms of challenges by itself, challenges of noise and interference that you have in sensing systems. And that actually pivots quite nicely to my talk, because I am going to talk about the issues of noise and interference in sensing systems, okay? And then the specific technique that I will work on today is absorption spectroscopy. So I also asked ChatGPT that what are the challenges in laser absorption spectroscopy, okay? And again, I think it does a pretty good job of picking up the key ideas there. Detection limit, interference, spectral overlap, sample, if you actually are doing sampling, calibration, and power consumption. I don't quite agree with the calibration part. Because I think you can actually make these sensors to be calibration free. This is what we try to do. But I think other points are quite relevant. So it's a useful tool. And actually some of these challenges that it has put out are the ones that we talked about in our recent review paper. Okay, so let's get back to the presentation now. And the rest of it is not prepared by ChatGPT. Okay, I'll start with some introduction and focus on environmental monitoring initially, then application of these methods to combustion, Then a new method that Imad has been developing on augmentation, and then end there. Okay. All right. So in contrast now to the previous talk was on aqueous systems. We are going to focus here on gas systems. Okay. So that's going to be the big difference from the last talk. Gas sensing has a lot of applications in our environment, in our daily lives. Okay, all the way from air quality monitoring to systems which does emit harmful emissions. Biomedical applications are there, and a theme that has been around for quite some time is that the way our nose senses different things. Okay, so we call it our biological nose, right? In the same way, you can come up with something called e-nose, electronic nose. Okay, so that thought has been there for some time. And the market size of such sensors is growing quite rapidly. This is just in some specific areas, medical, petrochemicals, or whatnot, is expected to reach 2 billion very soon. Okay, so when I look at gas sensing, we can characterize it in sort of these two axes of effectiveness, what is meant by sensitivity and selectivity, and then usability, which is, let's say, affordability and portability. So the gold standard in gas sensing is really mass spectrometry and gas chromatography. It's there in every lab. You bring in your sample, you do the analysis, you get the answer that you're looking for, right? But it's quite effective, but it's quite low on this axis of usability. Okay. On the other hand, a lot of people have been developing really tiny, small sensors based on semiconductor materials, membranes, electrochemical. So they are quite cheap and small, but they're not very good in terms of their selectivity and sensitivity. So I think that laser-based sensing sits somewhere in between as of now, okay, in comparison to these two extremes. And what we would like to do here in our group is to move it up in that upper right corner, and we think that hardware advances plus AI can really assist us to move there. In terms of hardware advances, there have been things happening already, and many advents are happening, but I will say a lot of focus is really on miniaturization. How do you make these sensors to be small and portable and have them go around the field rather than these being bulky and staying in the lab? Okay, so this has been a big focus in very recent years, miniaturization. But that and then their practical applications of such sensors in fields leads to some new challenges, which you may not see in the lab, or you have to at least pay more attention to them. So this includes noise, interference, again, the 2 points that ChatGPT also mentioned. But then there are other effects, like if temperature changes, how does that affect the performance of your sensor? Another one maybe I haven't mentioned here is humidity. Many of these, especially the small semiconductor sensors, get affected a lot in humidity, which can be quite high in Saudi Arabian climate. Maybe you're experiencing that, not so much now, but in the summer it's quite high. There are also effects on nonlinear blending, which are actually more relevant to liquids than they are to gas spectra, but something that you have to be aware of. Okay, so with that in mind, let me now show you some of our recent work where we have used machine learning and have seen some good results from it. So this example is on measuring BTEX, but just a quick introduction of the technique that we use. It's a very simple technique, Beer-Lambert law for absorption spectroscopy. You send a light source at a specific frequency, and the two intensities, the incident and the transmitted intensity, which gets absorbed by some molecules there at the resonant wavelength, are related by the Beer-Lambert law. And these are the important parameters here. The one that I'll highlight is that you have to know the absorption cross-section, and that's the way you can make this technique to be calibration-free and fully quantitative, right? And then the interaction length, path length is important. So eventually you're looking for this parameter. You're trying to get the mole fraction in a complex environment of gases. And the issue that I want to tackle today is when you have multiple species absorbing at the same frequency. So then it's quite simple. You just sum up this value, the absorbance from the multiple absorbers, let's say K absorbers, and you get the total absorbance. This holds quite well. This linear summation holds quite well for gases and dilute systems, but it has its drawbacks when you apply to more dense or more liquid-like systems. Okay, so why BTEX? This is a project that brought to us by the Environmental Protection Department of Saudi Aramco. BTEX are a family of aromatics which are have some toxicity if they are inhaled by humans, workers or whatnot in different facilities, and they're also important ingredients in many petrochemical facilities or functions. Okay. So the objective is to do selective sensing of these BTECs, but because their structures are so similar, benzene, toluene, ethylbenzene, and 3 isomers of xylene, this eventually leads to their spectra being also very similar and a lot of overlap. Okay, so this is their spectra. We are looking at relatively large wavelength range in the CH stretch region, and you see that their spectra are overlapping a lot. But we do see some differences in the shapes of their spectra, which is in this vibrational range, which is coming from, should not go to this meeting. Which is coming because of their, different vibrational frequencies and a little bit difference in their structure. But because we want to make this sensing portable, we cannot actually look at all of this spectra in the field, because we'll be using a small, tiny laser which cannot scan this entire region. So we'll actually focus on this tiny region here with a laser, with a tunable laser. And then if you look at it, this just looks pretty flat and quite hopeless in some ways, because these flat lines are just completely overlapping. But if we actually normalize the spectra, then we start seeing some pattern there. Okay, so it's just the normalized version of the same spectra. We see some pattern there, but still there's a lot of overlap. Okay, and what we will be measuring actually will be a summation of all of this. Okay, so the point is that how do we deconvolute that back to the contribution of these 6 species when we look at the composite spectra. So to do this further, we set up a simple experiment in the lab. We use a laser distributed feedback interband cascade laser at 3.3 micron. We send it through this sampling cell where air or the sample of BTEX will come in and go out, and then we look at the transmitted spectra. So to set up, we initially tried our regular methods, and we didn't get good answers for deconvoluting these contributions, as I will show in a bit. But this is then our machine learning algorithm. So we measure about 132 actual spectra experiments, but that's not enough for doing the machine learning. So then we add to that about 5,000 simulated spectra of these species. And we can do that because there's a database available, PNNL database, and because we can blend these spectra quite well according to the equation that I showed earlier. Okay. So then it's a relatively simple machine learning algorithm. We normalize it. We send it to a neural network. I think in this case we use 3 layers. We tune the model, and then we validate it later with 12 new spectra, which were not part of this entire training process. Okay. So then next I'll show you the performance of different methods we tried. So MLR stands for multilinear regression. So the axes are what we are determining and what was known for these mixtures. So it does a pretty bad job of finding these species. Sport vector machines slightly better, gradient boost much better, and then we get the best performance from these neural networks. So it's a regression job, but a pretty good regression job of separating out the contributions of these different molecules of very similar spectra. And we get a detection limit of about 8 to 46 ppm for this. But our sponsor said that detection limit is not good enough. We want to detect even smaller leaks. Okay. So then we have the selectivity, but we want to make the sensitivity to be better. So we do that with a technique called cavity-enhanced absorption spectroscopy. You basically make your laser light jump back and forth many times by using 2 highly reflective mirrors. This is the actual schematic of the setup, and that increases the interaction length. Okay, and so basically by doing this, your interaction length increases from a physical length of 5 centimeter to an effective length of 139 meters. So more than 3 orders of magnitude enhancement in sensitivity that you get, and this is what actually we see in our numbers that now our detection limit is down to 9 to 15 parts per billion. Okay, so that's pretty good and for this kind of a complex environment to detect all of these species with that sensitivity. And now we are working with with different partners to try to make this sensor portable, maybe mount it on a drone so that it can fly around and do the detection of these BTECs. Okay, so that was all environmental. So now we said, okay, we work in a combustion center, so how do we extend this to high temperatures? So for that, we use a shock tube as a chemical reactor. I will not tell you about the shock tube, how it works, those of you who don't know, because there's a lab tour today, okay? So I want to make sure you go to our lab and see the shock tube in action. But basically, it's our way of reaching high temperatures and pressures. It's the same sort of optical setup there, and we have reflective mirrors also on the shock tube to have this cavity process there, and so this gives us the high temperatures and pressures that we desire. This is where we don't have a database, okay? So room temperature, there are certain databases. High temperature, very little information. So we had to build our own database of cross sections, okay? So we do that by running a lot of shock tube experiments. So this is some raw signal, pre-shock, post-shock, and if I zoom into one, this will be an I0 signal, meaning incident, and then you get some absorption. So we do a lot of these experiments for those individual BTEX molecules. This is an example spectra measured at near 1200 Kelvin and 1 atmosphere in the shock tube. And so we build our database of these absorption cross-sections from about 1000 Kelvin to 13 Kelvin. And so then we can basically repeat the same process, very similar process, though we had to kind of change the tuning parameters of this model, but it's a pretty same process now applied to this high temperature environment. You get a bit more noise that I'll talk about it in a minute in these experiments. So if I look at the measured spectra here, again, it looks pretty flat here. This is a spectra which has contributions for all of these, from all of these aromatics. Okay, so it's a composite spectra. But then the normalized spectra shows some pattern which our machine learning model is able to use and decompose that to the contributions of the BTEX. So in this particular example, the 4 aromatics that we measure are in good agreement with what was known. And then we tried it on a number of other mixtures. So again, we get good agreement between what we measure and what was known. And in this case, our detection limits are of the order of a ppm. Okay, so that was still high temperatures, but non-reactive. There's no reactions happening. Okay, so again, combustion. We are interested in reactivity. So if you have some sort of a chemical reaction taking place, in this case, I'm taking the example of the pyrolysis of propane. So propane is going down at this high temperature, and then you have a number of other hydrocarbons being formed. Okay, so this becomes a complex system in the sense that to be able to understand this, you would like to measure all of these species. And, well, propane we understand quite well in combustion, but this would be useful for larger fuels or new e-fuels or whatnot we are developing. So it would be nice to have a diagnostic system which can follow all of these species at these time scales also. This time scale is of the order of milliseconds, okay? And so what has been done recently in the combustion community, for example, at Stanford University, is that in their shock tube, when they study this reaction, they will use multiple lasers and multiple detectors to follow the evolution of these species at different wavelengths, some in near IR, some in mid IR, and all that. But that is quite a complicated experiment to set up and to perform also with all of these lasers and optics going there. So the question we asked is that, can we make these experiments simpler by exploiting the knowledge that we have gained in machine learning and also the advancements in laser technology, which means basically rapid tuning of these lasers. So to look at this problem of propane as a toy problem, we look at the spectra of these hydrocarbons. Again, we choose a wavelength region where all of them or most of them are absorbing. Okay, so this is the CH stretch region. So again, we ran into the same problem that yes, we can detect all of them in a small frequency range, but they are overlapping quite a bit with each other. Okay, So we develop another database of their high temperature spectra, again performing individual experiments of each of these species, methane, ethane here, propane, and propyne, and ethylene, and so forth. Okay, so this is our own developed database of these spectra in this wavelength range. In these experiments, because these are reactive experiments and we don't have any opportunity to actually average the data, we have to make use of each scan of the laser. There's more noise that we have to deal with here. Also, in these experiments, it's a shock tube, so you have some vibrations happening, you have some beam steering or whatnot. So the noise becomes a bigger problem in these experiments. So we benefited here from denoising using autoencoders. We tried other denoising methods as well, but this is the one which gave us the optimal performance. So we've initially tuned it on a large sample of spectra that we utilized these spectra that we had measured. We added Gaussian noise to it of different levels, and then that's how we trained this autoencoder for denoising. And then we tested, so for example, these are different spectra measured at different signal to noise ratios, and on the right is their denoised versions, which is doing quite good job. Again, another example. These are 3 spectra that we measure in a reactive experiment, and the denoising algorithm shows us much better the features which are there. Okay, so just to show this further, we do a pyrolysis of ethane actually first, and then we'll go to propane. So these are the spectra measured. This is a composite spectra measured at different times in the shock tube: 0 millisecond, 0.7, and 1.5 millisecond. We send it to this pre-trained autoencoder, deep denoising autoencoder. It gives us our denoised spectra. Then we send it to, in this case, a multilinear regression model, which also has inputs of the database that we have developed. And then this gives us our contributions to the spectra from the species which are absorbing. Okay? In this case, we were looking at 3: methane, ethane, and ethylene. So the dots are our measurements, and the lines are some comparisons, which I show a little bit more on the next slide. So again, this is a case of ethane pyrolysis, propane pyrolysis. Here we are measuring actually, 5 species. And the comparisons are with some chemical models and also with some other experiments, the more complex experiments in literature, and we get a pretty good agreement. So this gives us confidence that this sort of method that we have can actually do a good job of measuring multiple species in this complex reactive environment. So what we are able to do is that, in contrast to this kind of multi-species setup used in literature, that we have simplified this a lot. Now we just use a single laser, and we get, if not better, but at least comparable performance to this very complicated setup. And I think this is enabled by machine learning, that we have really drastically simplified the setup, which I think opens up a lot of door for quick measurements and other applications. Okay, so that was all the case where we knew what to expect. Okay, we knew what interferences to expect, but real life, you don't know. So there could be unknown interferences. So this is where we use the concept of augmentation that Imad has been working on. So the idea here is that, again, we use a simple laser, and we want to detect maybe these 3 aromatics, but then there are others which are around there. But in this case, we don't know what those other aromatics are or what their spectra are like. So we would like to be immune to their presence, okay, without knowing them, okay? So the idea is that, let's say I want to measure these 10 species actually, okay, 10 different molecules, not just aromatics, water vapor is also there. These are my targets. And these are potential interfering species, but I actually don't know their spectra, okay? I'm showing it here just because we will use these spectra in the actual testing later on. But the idea is that these are unknown at the time when we start our process, okay? So the real world interference is unpredictable. So the way we do this is that we have a training data. We synthetically generate a lot of spectra, okay, of the targets that we have. So these are our targets, okay? And the interfering species, they will only come at the end for testing, okay? So we don't have any information on them during the training process, okay? So again, the observation is that when these will come, so in this case, we have blended the interfering species to the training ones, then of course the shape of the spectra change. If you just look at the green line, right, and others as well. So then how do we do this? How do we tackle this, this problem? Again, we use the concept of augmentation, okay? So the idea is that if you have this blue original spectra, which is known to you, okay, you do different mathematical operations on that. You flip it around, you mirror it, and you dilate it, okay? So these are three different operations that you do. And then we use these three sort of fictitiously generated spectra, flipped, mirrored, and dilated, as a training, as a potential interfering spectra that may come later on, okay? So this is something that we are generating some spectra. We don't know what the interference is going to look like, but we are generating these fictitious spectra as a way to anticipate the unknown interference, okay? So again, just to show this a little bit more, the way we do it is that in our training, we have, okay, this is the spectra of the target, okay? Then we add these synthetic fictitious spectra that we generated from mirroring and dilating and all that. And then in the testing, we have we add the interference of the spectra that I showed earlier, okay? But this was not part of the training, okay? So this could be quite different than that, and we use here a convolutional neural network based structure for this separation process, okay? So these are the final results. There's quite a bit going on here, but let me explain this a little bit. So let's look at the two extremes. So these are the 10 targets that we are measuring, mean absolute error, okay? Known means that you already knew what the interfering species are going to be, okay? So of course this is the best performance. None means that you did not know anything about the interfering species, and then you still try to measure your target species, so the absolute errors are actually quite high, okay? And then as we add the flipped version of the known spectra, mirror, dilate, and then all of that, and then all with some fine-tuning, we progressively decrease the absolute error a lot, okay? So I think this is quite a powerful concept in terms in anticipating unknown scenario, okay? So these augmentation methods help us sensing in these real-world real-world scenarios with unknown interference as well as noise, okay? So this is just another way of showing the same thing in a heat map. So these are our targets. These are the interfering species that we again tested on later. So again, the dark colors means really low absolute error, okay? The lighter colors a little bit more error. And we can also then understand this, that why in some cases the error is a little bit high. We can also look at that in terms of just the molecular fingerprints of these species. So these are the results from our machine learning model, but here we are just looking at the similarity of the molecular fingerprints of these species. And so the two plots not exactly the same, but they sort of are in the same region, and so they help us understand that basically where the performance is less is where you have more overlap of the spectra. Okay, and so that's kind of what we understand. So this could be used as a qualitative way of anticipating the performance. We also looked at this at different noise levels, so 20, 30, and 40 signal-to-noise ratios. Of course, as the signal-to-noise ratio increases, the map becomes darker, meaning better, okay? So smaller errors. And some of these species are actually immune to even at low noise levels. We get pretty good performance here because these are features like methane and ethylene, which have very sharp features, so they are not affected as much by the presence of interfering species. Okay, so the last thing, maybe I'll take a couple of minutes, so far what I've shown is the sensing of different species in the presence of a lot of interference and noise, but we have also utilized spectral information to predict fuel properties. Okay, this is the work we did a couple of years ago, actually, so we can use the spectra as a way to predict fuel properties, different kind of properties we have looked at. So the idea here is that, again, you start with a database of individual spectra of a lot of hydrocarbons. We combine them together through a linear summation, weigh it according to what you expect them to be in a real fuel environment, okay? So then you create these blends, and then we later on test it on real fuel blends or their surrogates, and those are represented by their Peona split of these real fuels, which is these naphthenes, aromatics, oxygenates, olefins, and whatnot. Okay, so the structure is that you assemble this database. We also do PCA in this case to reduce the dimensionality, and then we use the neural networks to untangle basically the synergistic and antagonistic effects that you have when you blend these different functionalities of aromatics and oxygenates or whatnot. Okay. So in these two works, we basically showed the prediction of RON, MON, sensitivity, DCN, and C by H. These are our absolute errors, which are quite comparable to the experimental uncertainty of these methods you have. This is just an example of the DCN prediction that we did. Okay, so I'll try to wrap up. So in summary, I'll first say that the laser-based sensing is a very powerful tool for practical applications, environmental monitoring, air quality, chemical environments. And I think what we have seen in these 3 days of this conference is that you can do more from less by using machine learning methods. Okay, that's kind of what I look at it. Of course, you have to be cautious that the results make sense. Okay, so in our work we have shown selective and sensitive sensing of BTEX and a very simple optical setup to do multi-species sensing in complex chemical environments. And then the augmentations are really helpful in looking at unknown interference and noise in real-world applications. So I think the spectroscopy is quite universal because what spectra really represent the structure of molecules. Okay, but it's a quick and easy way of understanding those molecular functional groups that you have. So once you have this sort of a spectral information, you can send it through different algorithms, and you can look at not just the properties that I showed, but many other aspects or many other properties of blends and fuels and other applications, which kind of this slide shows it nicely, that once you have that kind of a universal sensing platform, and this is where we are going, it has numerous applications, unlimited applications for environmental monitoring, also many things in health, security, and others. So this is quite a powerful tool in that sense. Okay, so I will end here, take any questions.
Thank you very much. Got time for a couple of questions, if there are any. Right. Somewhere there's a queue.
Good talk, Aamir, as usual. So just a curiosity about the augmentation method. So is there a sensitivity to what the amount of data of fictitious data that you include in all of this? Is there a sweet spot, let's say, to be in, or the more you put there, the better it is?
That's a good question. I think at some point in time, after a while, there's no further. From what I remember, we looked at that actually. Is that there is a sweet spot. After a while, you don't get much advantage of keep adding more and more. So there is like diminishing return after a while.
But it doesn't get worse.
Maybe Ahmad can confirm. Ahmad, did you check that? Yeah, that's okay. No, it doesn't get worse.
Thank you.
One more question. Thanks.
Excellent talk, Aamir. Now, uncertainty in quantification. It's easier to take, here's an experiment and this is my error. Now, you're doing a lot of things to the spectra. Is there any risk that we altering, we changing, we actually getting the right answer for the wrong reason?
Yeah, so we have looked at uncertainty in these systems, especially when now we are sending these spectra through machine learning models and all that. So the estimation of uncertainty is definitely a bit more challenging, but we have tried to do that, and definitely the uncertainty increases. And I didn't mention it today, but in our papers we do include that. So just as an example, ballpark number, if I'm just doing my regular absorption experiment and I account all of uncertainties, we typically say we can do this with 2 to 3% uncertainty, the mole fraction. But once we send it through these complex algorithms and all that, they add their own uncertainty. So it can easily, the uncertainty from those 2-3% level go up to 7, 8, 9% levels, right? So it does increase the uncertainty, and we have looked at that. So I guess that's the short answer.
So you are able to quantify it?
Yes.
That's what matters.
Yeah.
Okay, one more question.
Thank you, Aamir. I think the initiative is very great. in terms of improving the precision of the measurements. So do you have a plan to take it one higher level by focusing in the behavior of the reactions and predictions, the result of the analysis?
So this is specific to reactions, you mean?
Exactly.
Yeah. So I think there are different ways of doing that, and there were some talks about it. This is like doing chemical kinetic modeling using data science, right? I guess that's there. So there's a lot of efforts happening on that. You can look at the contributing reactions. There was also a nice talk in on the first day on putting physical insights into these reactions. Okay. So yes, I guess the short answer is that you can use machine learning, data science-based methods to look at individual reactions, but also some of these reactions, which makes a complete model. And this is happening in our community on many different fronts. Okay. Or maybe we can talk later more.
Okay, thank you very much. If we thank our speaker again.